Good day everyone. Welcome once again to our next video for our next example uh, taken from our example from the physics. Alright, so this time we are going to solve this another example class, example number 3. An engineer is designing the runway for an airport. Of the planes that will use the airport, the lowest acceleration rate is likely to be 3 meter per second squared. The takeoff speed for this plane will be 65 meter per second. Assuming this minimum acceleration, what is the minimum allowed length for the runway? Okay, so that's our next problem, or example number 3. So actually class, this example is just similar to the second example that we have just solved in the previous video. So you have two ways of solving this problem, either by using the first two formulas of the uniform acceleration, or you can go directly to formula number 3. Anyway, I will show you the solution of both of the solutions. So again, first we need to write down what are the givens in this problem. So in this problem, we have acceleration rate. Which is given as 3 meter per second squared. Alright, so we're given the acceleration, which is 3 meter per second squared. So this is the lowest acceptable acceleration rate. Next, we have, what's the other given? So takeoff speed. So we're given takeoff speed, and this is equal to 65 meter per second. So what does it mean, takeoff speed? So how do you understand that, class? So if this is the runway, all right, so t equal to 0, it means that the plane is at rest, it's not moving yet. So it means that the velocity here, the initial velocity, is equal to 0, right? So takeoff speed, it means that it is the speed. Okay, so we have here t equal to a certain value which we don't know yet. So at this point where the plane will take off, okay, so at this point where the plane takes off, so we have what we call the takeoff velocity. So we can call this as TO for takeoff velocity, and we can let this be equal to V in our formula. Alright, so at this point here where the plane will stop or start flying, so at this point the velocity here, the takeoff velocity, is equal to the V, which is the final velocity when the plane takes off. Alright, so we have to analyze this problem that way. And before we continue that one, so we have to write down what's the given. We have the takeoff velocity, we have V, which is equal to 65 meter per second. Alright, and what is required in this problem? What is asked in this problem? So it says that assuming this minimum acceleration, what is the minimum allowed length. So what does it mean? Length. Minimum allowed length. So what does it mean, class? Length. So length refers to this runway. Alright, so this is the runway. So this is what is being asked in the problem. It means you are asked to solve for the displacement here. This is the minimum length allowed. Okay, so we are asked to solve for the displacement, minimum allowed length. Alright, so for our solution, once again, I'd like to suggest that it's better for you to write the 3 formulas for the uniform acceleration over and over again, to help you memorize them or remember them. Alright, so we have the formulas. We have the final velocity v, in this case our takeoff velocity, is equal to the initial velocity v sub 0 plus the acceleration times time t. Then the displacement s, or in this problem we have what we call the minimum allowed length of the runway, is equal to initial velocity multiplied by the time t plus 1/2 times the acceleration times the time squared. Okay, and then another formula, we have the square of the final velocity v squared equal to the square of the initial velocity, then plus twice the acceleration multiplied by the displacement. Right, so these are the formulas that we need to remember. Okay, so you can, as mentioned earlier, we can use these 2 formulas, either these 2 formulas, or you can use directly this formula. Now I would like to show you the solution using these 2 formulas, using this analysis class in our illustration. So at t equal to 0, it means that the plane was at rest, it's not moving yet, so the initial velocity is equal to 0. So when it moves, and then finally at this point where the plane takes off, so this is the final velocity so that it can take off. So VTO, the takeoff velocity, which is equal to V. Okay, so if you know the time, when this time, what is the time when the plane reaches at this point where it takes the or it takes off, then you can use, or you can calculate this distance, this is the minimum allowed length, by using this formula. So you just need the time t here, because acceleration and also the final velocity is also given. Alright, so using this formula, so as mentioned, at t equal to 0, our initial velocity is equal to 0. Alright, so at t equal to 0, our initial velocity is also equal to 0. So therefore, from this formula, we have v equal to v sub 0 plus a times t. So v is given, and that is 65. Okay, so we'll just omit the unit first, and then initial velocity is 0 plus the acceleration, which is 3 meter per second squared, multiplied by t. Alright, so this is the resulting equation or expression now after our analysis here. Then from here, we can solve for t. Now divide both sides by 3. So we have 3t equal to 65. Or just change the position class, transpose, so it becomes both negative. So divide both sides by negative 3. Or just divide both sides by negative 1 and then divide by 3 both sides. So we got t equal to 65 divided by 3. And our t here is equal to 21.67 seconds. Alright, so we have solved now the t, and we can solve for the displacement s, or the minimum allowed length, by using the secant formula here. So using the secant formula, we have s equal to v sub 0, or initial velocity, multiplied by time, plus 1/2 times a, the acceleration, times the square of the time t. So substituting, so again at t equal to 0, v sub 0 is equal to 0. So the whole thing here becomes 0. So s is equal to, this becomes 1/2 times a times t squared, or s is equal to 1/2 times the acceleration, which is 3 meter per second squared. Alright, then multiplied by the time, which is 21.67. This is squared. Okay, so the unit of acceleration is meter per second squared. We have the time here in terms of seconds, but this is squared. So secant squared, you have secant squared, and you have secant squared at the denominator, because this is per second squared. So secant squared divided by secant squared, so that becomes 1. And the remaining unit is in terms of meters. So from here, substituting the values, calculating, we got s is equal to 704.16 meters. Okay, so this is the solution to this problem. And as mentioned a while ago, you can use also this formula, not to solve directly for s. Okay, so from this formula, we have v squared equal to v sub 0 squared plus 2 times as, and we know that the initial velocity is equal to 0, so the whole thing here, or this term here, becomes 0. So what is left is v squared equal to 2 times as. So solving s, divide both sides by 2a, so s becomes v squared over 2 times a. And substituting the given values, so we get s equal to, okay, so substitute it here, our v, which is 65 meter per second. So 65, then you square this one, divide by 2 times, the acceleration is 3. So when you use your calculator, 65 squared divided by 2 times 3 is 6. So it gives us same value, 704.16 meters. Alright, so these are the solutions for example number 3. Okay, so I hope you were able to follow our solution class and able to understand. So it depends on which formula that you're going to use. So if you analyzed well the given problem, then you can easily identify which of the formulas that you need to use. Okay, so thank you very much and hope to see you again in our next video. Bye.